Ian has been a master's student here for 2.5 years. And before that, he got his bachelor here as well. And it feels like I've known Ian for a really, really long time. And, I checked my emails, it's actually true. The first email I got from Ian was when he was still in high school. And he expressed interest in the renewable energy project. So that's how we first connected at a Human Exchange, but then we didn't really connect again until maybe 2 or 3 years later, leading up to grad school. I think it's also very fitting that you had to walk through the ocean engineering lab to get here. So we saw you had to pass a bunch of stuff that goes in the ocean. And Ian has done some really, really nice work over the last 2.5 years, both designing, analyzing, and then building and deploying a tidal energy turbine deployment system for Memorial Bridge, which is sort of a prototype for an estuary bridge. And we have 1 journal paper submitted on this, a second one in progress. And with that, I'll leave it to me to tell the story.
Okay, thanks, Martin. As Martin said, my name's Ian Gagnon, and today I'll be talking about the hydrokinetic turbine deployment system that I designed for the Memorial Bridge. I want to take a brief minute to thank my thesis committee. I've worked really closely with Martin and Aaron. They're on this project, and then Rob was also a source of guidance throughout the project as well. So this is the outline for my talk, and this outline briefly follows, or approximately follows, the outline for my written thesis as well. So I'm going to first start off talking to you about the Living Bridge project. So this is a picture of the Memorial Bridge, and the aim of the Living Bridge project is to convert the Memorial Bridge into a self-diagnosing, self-reporting, user-centered smart bridge. And the way that we're going to do this, the way that we've done this, is we've attached structural health monitoring sensors to the bridge. And then in the river, the Piscataqua River below the bridge, we've deployed estuarine sensors on a floating platform. And then soon we're going to deploy a tidal turbine to power the sensors in a portion of the bridge.
I have a question.
Yep.
It looks rusty.
I think it's just due to the...
is that the old bridge? Or is that
nope, this is the new bridge.
That's the new bridge?
Yep. I think it just looks rusty because of the way that the light's hitting it. This picture I think was actually taken at like 5 a.m. in the morning on a, like just as the sun was rising. So it kind of had like a reddish light, but it's not really rusty. Yet. So why do we want to do tidal energy at bridges? There's a few reasons why we think bridges are favorable locations for tidal energy deployments. First, bridges are typically constructed at constrictions in rivers where there's a shorter distance to cross the river. And at constrictions in rivers, the flow tends to speed up. When the flow speeds up, we can generate more power. Bridges also typically already have their own environmental permitting. And we thought that we could deploy a tidal turbine at the bridge, and since the tidal turbine would be a part of the bridge structure, we could piggyback onto that environmental permitting and reduce our own permitting effort. Existing bridge structures could also be used as strong mooring locations, and the power generated from the turbine we thought could more easily be transmitted to shore via the bridge than a subsea cable. So why do we want to do tidal energy at the Memorial Bridge? Well, this map up in the upper right-hand corner here shows a view of the Great Bay Piscataqua River estuary and the surrounding towns. Here's Durham. The Chase Ocean Engineering Laboratories is at this dot here. We're about 20 miles away from the Memorial Bridge, which connects Portsmouth, New Hampshire to Kittery, Maine. It crosses the Piscataqua River, which drains the Great Bay into the Gulf of Maine. If you look into this map here, it's a zoomed in portion of that map. You'll see that I've marked locations of infrastructure that makes the Memorial Bridge an ideal location for a demonstration tidal energy deployment. Locations such as these are on land construction locations that could be used for construction. There's commercial marine construction services located at this point. The Portsmouth Naval Shipyard is located here. Strawberry Bank and Prescott Park are two large areas where lots of people gather and will be drawn towards a project like this. This H marks a really good viewing location for the deployment site, and we have locations where we can take the platform out in the event of an emergency. So I just have a few vocab words that I want to introduce to you about tidal currents. First, ebb and flood tides. So when the tides are flowing out towards the ocean, we classify these as ebb tidal currents. And then when the tides are flooding in towards the coast, we classify those as flood tides. Flood tides are when the tides are rising, and ebb tides are when the tidal elevation is falling. Now, once a month, we have what are called spring tides, which is where you see elevated tidal, like extreme tidal elevations, as well as extreme tidal currents. And then for the other portion of the month, we have what's called neap tides, which is where the tides are less strong and they're kind of dampened out. So now I'm going to talk to you about the resource characterization that we performed for this site. So why do we need to perform a resource characterization? What did we know before we did this resource characterization? We knew that we'd been out to the site and we'd kind of looked at it and it looked like this. So we kind of thought, yeah, it seems like the currents are kind of flowing fast, but we didn't know exactly how fast. We knew from a U.S. Army Corps of Engineers report that Portsmouth Harbor has the fastest currents in a navigable harbor in the Northeast. So that was another positive indicator that tidal energy conversion could be possible at this site. And we also knew from an openly available tidal energy resource assessment that was performed using some numerical modeling around the entire United States that we had estimated mean currents of around 1.2 meters per second. So that was also another positive indicator that tidal energy conversion could be possible at the site. But we still didn't know how much energy could be converted by a turbine of a given size. We didn't know the spatial variation of the currents at the site. We didn't know where we should put the turbine, if we should put it on the Portsmouth side or the Kittery side of the bridge. We also didn't know about the temporal variation of the currents. We didn't know if the currents would be too slow at times and we would need to provide energy storage in order to provide constant power. And we also needed to better understand what the fastest currents are such that we could design the structure. And being in an academic environment, we needed to publish something. So we decided this would be a good thing to write a paper about, and we recently submitted this paper to the IEEE Journal of Oceanic Engineering. So how do we measure tidal currents? To measure tidal currents, we use a device called an acoustic Doppler current profiler. It uses sound to measure a profile of the currents throughout the water column. So the first acoustic Doppler current profile surveys I'm going to talk to you about were performed by Tom Littman using his CBAS system. The CBAS was driven by a great driver, John Hunt. What we did when we performed these surveys was John drove the jet ski. The CBAS is also sometimes called the jet ski. We drove the jet ski along these transect lines. And during a flood tide, we measured the currents throughout the water column and across the river. We also did the same thing on an ebb tide at this location. And then these charts show the velocity magnitude throughout the depth of the river and across the river, whereas these arrows on these lines just show you the surface currents. So the first thing that I want you to notice is this is the location that we ended up ultimately selecting where to put the turbine. But if you look at the Portsmouth side pier, you'll see that the flood currents are much weaker near the surface than the ebb currents. And then on the Kittery side pier, the ebb currents are much, they're approximately the same as the flood currents. And you can also see that from these charts, and that same trend follows for a good majority of the depth of the river. So we need to decide where to put the turbine. Inside the two bridge piers was basically off limits. We couldn't put a turbine there because that's the shipping channel, and we needed to allow shipping traffic to pass through there. And we ultimately decided to put the turbine on the Portsmouth side because it does offer greater speeds than at the Kittery side. And we also thought that the Portsmouth side, it's closer to downtown Portsmouth where more people are likely to view the turbine. And this is a demonstration project, so you'll be able to see the turbine.
And it's in New Hampshire.
And it is a New Hampshire-based project funded by the New Hampshire DOT. So yeah, there was a lot of factors that pointed towards the Portsmouth side. So that kind of looked at the spatial variation of the currents. Then we performed, well, I didn't perform, but I used the data from 2 acoustic Doppler current profile surveys that were bottom deployed and upward looking. The first survey was deployed at this location in the center of the bridge pier as a part of a NOAA NOS survey of the currents throughout the entire Piscataqua River and Great Bay. The second survey was performed as a senior design project here at UNH with the intent of this project happening in the future. And then the green pin here shows the location of where we're going to deploy the tidal turbine. So the data from these surveys, this pin represents that data, this pin represents that data. The way that you read these compass plots is the direction is plotted circumferentially and the magnitude of the velocity is plotted radially. So I'll then plot these plots right over the map. And what you can see is at the Higgs and Griffiths location, you have that imbalance in ebb and flood currents, whereas it's much more balanced at the center of the bridge pier, at the center of the bridge. And you can also see that in both of these locations, the flood and ebb currents are approximately 180 degrees opposed to each other. So then I wanted to calculate some time average metrics that could be used to characterize this site and compare it against other tidal energy sites anywhere else. So for the first parameter that I calculated was the mean kinetic power density. This parameter tells you how much power on average you can convert from the tidal currents with a given rotor size. The second parameter I calculated was the mean kinetic power asymmetry, which tells you how much power on average is available in your ebb tides compared to your flood tides. And you'll see that at our site, we have ebb tides that are approximately 5 times more powerful than our flood tides. I also wanted to figure out what the peak velocity was for calculating those structural loads. And I wanted to quantify that directional asymmetry between the flood and ebb tides. And for us, it's about 4 degrees. So then we needed to select and size a turbine. So to do that, one of the main things that we were interested in was how much energy could we generate from this turbine. So a senior design project suggested that in order to power the Memorial Bridge and some of the estuarine sensors, we would need to produce about 1 megawatt hour per month. So the power equation is given over there. CP is kind of an important parameter. That's the coefficient of power or the efficiency of the turbine, how efficiently it can convert the linear motion of the tidal currents into rotational motion of the rotor and turn that rotational motion into electrical energy. If you integrate power, you get energy. And I use those equations to create these curves on this chart. So what this chart is showing is the expected energy production over the course of 30 days compared to different turbine swept areas. And what the different lines represent is different turbine specifications. So different coefficients of power for turbines and different cut-in speeds for turbines. A really good turbine will have a very high coefficient of power and a very low cut-in speed. Cut-in speed is the speed of the currents that it starts spinning and generating power. So these all lines represent kind of a range of turbine operating parameters. So we selected a turbine in the middle range, a coefficient of power 0.35 and a cut-in speed of 0.7 meters per second. And for that kind of average operating parameters, we figured out that to produce 1 megawatt hour per month, we would need a turbine rotor size of about 6 meters squared. So once we knew how big of a turbine we needed, we then had to determine what type of turbine we wanted to use. There's a couple different types of commercially available tidal turbines. This doesn't even show all of them. Unlike wind turbines, tidal turbines haven't converged on a best solution yet. There are types that represent your modern wind turbine very closely, the axial flow, horizontal axis turbines, such as Vernon Power's kinetic hydropower system. But then there's other turbines that look quite a bit different. Ocean Renewable Power Company uses a cross-flow horizontal axis turbine. And then these two companies, InStream Energy Systems and New Energy Corporation, use a vertical axis cross-flow turbine configuration. So originally we selected InStream Energy Systems to provide our turbine, but then due to financial circumstances at InStream, we changed our turbine provider to New Energy Corporation. And we've been working with them since November to provide our turbine. So yeah, we selected a cross-flow vertical axis turbine. The advantages of this turbine configuration are that it allows us to place the sensitive components of the turbine above water, where we don't have to worry about them getting flooded, or we don't have to worry quite as much about them corroding. The rotor doesn't need to be yawed to angle it into the direction of the flow to efficiently convert those tidal flows in different directions. The commercially available models in this configuration were typically placed near the surface, which is something we wanted to do, as this would be a demonstration project. We wanted people to be able to see it. UNH has experience modeling these types of turbines, both here in the ocean engineering labs and in the field, and as well as numerically modeling these turbines. And these turbines were commercially available in that kind of 6 meter squared size that we needed. I should also mention that the system was originally designed for the InStream Energy Systems turbine. It's since been adapted to allow the deployment of the New Energy Corporation's turbine, and I think it does have potential to deploy any configuration of turbine. So once we had a turbine selected, we needed to estimate how much energy we could produce in 1 year, or what we like to call the annual energy production, or AEP. And the way that you do this is you first figure out the distribution of your tidal speeds, the frequency that each tidal speed occurs. So you plot a histogram. This is for the Hicks and Griffiths location, whereas the histogram over here is showing the distribution of the tides at the Commeror 07 ADCP deployment. What you can see from the Hicks and Griffiths deployment is a very bimodal distribution, and we get that bimodal distribution because of that really high mean kinetic power asymmetry. We get flood currents that are very different than our ebb currents, whereas at the K07 site, the ebb currents and flood currents are very similar, so you don't get that bimodal distribution. Once you have your histogram figured out, you can then figure out your turbine's power curve. The power curve, the way the power curve works is you have vertically the power that can be provided by your turbine at different tidal current speeds. You can see here that the turbine cuts in at about 0.7 meters per second, and it starts to generate power, and then it generates power until some speed where it has to cut out and not produce any power in order to not destroy itself. Essentially, when you're figuring out the annual energy production, you're multiplying this power curve through your histogram. You're taking the power that's available at the different velocities and multiplying it by the frequency of those velocities, and then normalizing it by the amount of hours in a year. For our site, we determined that about 10,000 kilowatt hours could be produced in 1 year. So then we needed to figure out what we were going to do with all that energy once it was generated by the turbine. So we figured out there was a couple different ways that we could manage the energy after it came off the turbine. A very simple way of doing this would be an off-grid solution where the turbine would remain completely off-grid. We would never supply any power to the grid, and we wouldn't rely on the grid for any power. Any power that the turbine produced could be used to power a load, such as our instruments in the bridge. But then when the turbine produced too much power, the power would have to be dissipated through a load bank. A slightly more complicated, this system has the advantage that you don't have to deal with any permitting with the utility, but it has the disadvantage that you're not going to utilize a lot of the power that the turbine produces, because a lot of the time the turbine will be dissipating power through the load bank when it's producing too much power. And then a lot of times when the turbine isn't producing that much power, you won't be able to run your load. So you'll have to shut down your load. You can maybe do a little bit better than this situation with an off-grid system with a battery. That'll help get you through some of those times where the turbine isn't producing that much. And then a system that we considered quite in depth was an automated transfer switch system. An automated transfer switch is a common electrical component that's used in residential applications for backup generators. So when the utility grid goes down at your house, if you have a backup generator, you have an automated transfer switch that automatically switches your house to the backup generator, and then your house continues to run. So we thought a system like this could be possible at the bridge, and it would allow us to not have to go through the permitting effort required if we wanted to hook up to the utility grid power. And I started, I'll talk about it in a bit more. But the other configuration that's also possible is a system such as what is used for residential photovoltaic solar applications, where you net meter and use a bidirectional meter. When the turbine or your solar system produces too much power, more than your load is consuming, you put that power back out onto the grid. Your meter runs in reverse. You actually get paid for that energy that you produce. And then when your turbine or photovoltaic system is not producing enough power to power your load, the grid supplies the power needed to power your load, and your meter runs forward and you get charged for that electricity. So I was interested in the possibility of this automated transfer switch scenario, and what I was really interested in is what turbine size should we select for a given load, the resource that we have, and a given battery bank size. So I created a simulation that simulates this automated transfer switch scenario. The first thing on this upper plot, which shows power on the vertical axis and time on the horizontal axis, is the power consumption. We assumed a constant power draw based off of the estimated energy required to power the bridge for 1 month, and that's represented by this red line here. I then simulated the estimated power production of the turbine by this blue line here. That power production curve was created based off the acoustic Doppler current profile survey data. Then after producing those two curves, I could then figure out our battery charge state, which is shown in this curve here. And then I want to draw your attention to two specific areas in this time series. The first area right here occurs during a neap tide, so that's when the currents aren't running as fast. And when the currents aren't running as fast, we're not producing as much power. And during that time, the battery gets empty at a few different times, and we underproduce. So wherever there's black lines here, that's where we're underproducing, and that's how much power had to be supplied from the grid to make up for the underproduction of the turbine. Also, during spring tides, when the tides are running really fast, the turbine is producing a lot of power, and we only have a finite amount of storage in our battery, and eventually our battery will get full. So when the battery gets full, we still would have to shed that power because we weren't hooked up to the grid, because we didn't want to hook up to the grid because of all the permitting effort it would require. So these pink lines show the amount of power that we are overproducing at those times when the battery is full. So like I said, I was interested in what rotor size battery bank would be most correctly sized for our power consumption and the tidal and the power production estimates. So what I did is I ran that simulation shown in the previous slide for multiple different rotor areas shown on the horizontal axis here, and battery bank sizes shown by the multiple different curves in this plot. And for each one of those surveys, we calculated a parameter that we invented called the utilization factor. What the utilization factor is it normalizes the total amount of energy generated by the turbine by the amount of energy generated by the turbine to do useful work, plus the amount of energy dissipated when the turbine was producing too much power, plus the amount of energy drawn from the grid or a backup source when the turbine wasn't producing enough power and the battery was empty. So what you can see from this chart is that if you don't have a battery, the system does not perform very well at all, and you have very low utilization factors, meaning you're utilizing a very small portion of the energy that you're generating. Even with a really small battery, such as this 500 watt-hour battery shown by this yellow curve, a 500 watt-hour battery is about the size of your car battery. It's not even really designed for this application. But you actually start to utilize a small portion of the energy, around 30% if you match your rotor to the right size. Then once you work your way up into kind of an appropriately sized battery bank size, around the 10 kilowatt hours, that's what a Tesla power wall is. That's a residential energy storage device. You actually start to see pretty decent utilization factors in the 75% range. But we should also notice is that as you increase your battery bank size past this battery bank size, there's diminishing returns. You see that the largest battery bank size is 200 kilowatt hours. That's a massive battery. That's probably about utility. That's a small utility size scale battery. So there's diminishing utilization factor returns. I did test the sensitivity of this model with respect to the initial battery bank charging state, and I found that the model is very sensitive to initial charge state of the battery if you use a very large battery. But if you use a very small battery, it's not very sensitive to the initial charge state. Ultimately, though, this system was deemed infeasible because, first off, we would need a ridiculously large size battery in order to utilize all of the energy produced. And just some of the components that would be needed to implement a system like this aren't readily available off the shelf. And it wasn't an area of the project where we wanted to focus our efforts to actually deploy this system. So we ended up selecting a grid-tied net metered system where we would always have a utilization factor of 100. So I then had to deploy or design and analyze the deployment structure. So we determined that we would use a floating platform design for a few reasons. This design would allow the turbine to be easily floated in and out of the site for maintenance as well as switching out turbines. It also gives an easy location where the turbine can be researched, as well as maintenance can be performed on it if the turbine is floating at the surface. It's also visible to the public if it's floating at the surface. And UNH has experience with past turbine deployments in this configuration shown in these photos below. So this is an image of the turbine deployment platform. It's about 50 feet long, 20 feet wide. The turbine or the platform floats on two HDPE foam-filled pontoons that are connected together by a steel I-beam structure. It floats up and down the tides on these pontoons and is connected to two vertical guideposts using two pile guides. As the currents flow horizontally, it rotates the turbine. So the first calculations that I needed to do was to determine how much buoyancy we needed for a platform of this type. The buoyancy has to be at least equal to the weight of the platform. hopefully slightly greater than the weight of the platform in order for it to stay above the water surface. So the buoyancy force is equal to the weight of the fluid displaced, and the weight of the fluid displaced is equal to the volume of the fluid displaced times the density of the fluid. And I've calculated those parameters in the highlighted sections to the right. I then needed to calculate what forces would be exerted on the platform, first from currents and wind. We needed to make sure that our moorings would be greater than these forces that are exerted on the platform, such that the platform wouldn't rip off the bridge. We used the drag equation to determine the drag force on the pontoons as well as the turbine due to the tidal currents, and then the drag force from the wind from the entire above water structure. If you perform basic statics, you sum the forces in the x, the forces in the y, and the moments about some points. They all have to be equal to 0. Then you can determine your reaction forces. And surprisingly, the platform, I've been out on it when the tides are running on it, and you can see that the forces are being absorbed into the vertical guideposts in kind of in the exact directions that you would expect these reaction forces to occur. We also had to determine what the wave forces on the structure would be. Typically, you determine wave forces using Morrison's equation. The density, the displaced volume, and the area are parameters that are pretty easy to determine based off the circumstances of your problem. The orbital velocity as well as the orbital acceleration of the waves are also fairly easy to determine based off airy linear wave theory. They're given by these equations. The tricky part of using this equation is determining your coefficient of drag and your inertial coefficient. So the way that's typically done is by fruit scaled model tests. And in a fruit scaled model, what you do is you match the ratio of your gravitational forces to the ratio of your gravitational forces to your inertial forces in your model to the ratio in your prototype. So we did construct a 1 to 13 fruit scale model as a part of a senior design project, and that model was used for seakeeping analysis under tidal current loading, but we weren't able to determine the wave loading conditions for our platform from that model. Instead, we used some data from the literature given by this design guide, where you use these curves to figure out what the force on your structure is. The way you use these curves is you figure out the displacement of your structure. You also need to determine what wave height you're going to use and what draft your structure has. Then if you know what wave height you have, you can figure out the wave force per displacement. You then multiply that by the you multiply the wave force per displacement by the displacement of your structure, and then you need to multiply it by what's called a body length adjustment factor, which is found using this plot, where you determine the relative body length of your structure. It's the length of your structure compared to the length of the waves, and then you multiply all those parameters together and determine the force of your structure. So we use this force to determine what the loading from our platform onto the vertical guideposts is. We also needed to ensure that our platform would be stable. The thing that we were most concerned about was this bow down or pitching angle. So this bow down angle, it would be caused by either uneven distribution of weight on the platform, as well as the drag load on the turbine rotor. So to determine this bow down angle given by theta, we first had to determine the metacentric height, which is the distance between the center of gravity and the metacenter of the platform. And you can do that by figuring out your area moment of inertia, the displaced volume, and the distance between your center of buoyancy and center of gravity. You could then determine your bow down angle by figuring out what your pitching moment is, which is the combined moment created by these two forces, and then dividing it by the metacentric height and the weight of your structure. And these are the various different configurations that I calculated, and this was the design bow down condition. I also had to design a turbine pitching mechanism, which is the structure that holds the turbine and rotates it in and out of the tidal currents. It was designed to mount a turbine bigger than our turbine in our design conditions. It can also deploy and remove this turbine in the designed tidal currents. It's actuated by a winch that's got a 12,000 pound tension rating, and its IP rating is 6.8. That means that you can essentially use it pretty deep underwater, be controlled wirelessly. The whole thing pivots on some 3,500 pound rated rollers in these beam cradles, and these rollers use sealed stainless steel ball bearings for corrosion protection. I also had to consider a multitude of other things when we designed this structure, and if you want, you can ask me about them in the Q&A session. We then had to get everything fabricated. So the turbine deployment platform frame was fabricated by Ace Welding in Merrimack, New Hampshire. It was then brought down to Duncan Galvanizing in Everett, Massachusetts to be galvanized. It was assembled at the New Hampshire Port Authority, where the pontoons came up from Kentucky to join with the frame. Pepper Cove Marine performed this. We then had to deploy the platform. It was flown into the water by Morse crane and then towed to the Memorial Bridge by Pepper Cove. And this is it on the first day when it was deployed. And it was looking pretty good until this happened, and it was not looking very good. So what was happening at this time was the tidal currents were flooding. We were in a spring flood tide. So the tidal currents were rising. And as the tidal currents were rising, our pile guides weren't allowing the platform to rise. So the pile guides were actually binding up on the vertical guide posts. So the reason why we had selected these pile guides was because they were made of standard rigging equipment. And we thought that it would be a good design and help to eliminate a lot of risk in the design, because we would use just rated components, and we could just rely on the ratings of the components rather than our own analysis. The issue with these components is that they didn't let it rise. So Martin and I spent an afternoon, looking around the New Hampshire seacoast at pretty much all of the pile guides on the entire coast. And we ended up coming up with this design based off of all the different designs that we saw. This design uses a rigid square hoop structure to support 8 rollers on each pile guide, and then there are backup rub plates in case any of those rollers fail. Over the past few months, we've also had the fabrication of the turbine pitching mechanism completed and assembled at the UNH Pier by Pepper Cove Marine. And the platform is relatively close to being ready for a turbine right now. So in conclusion, a turbine deployment system has been designed and is ready for a turbine to be installed on it this spring. The turbine will be installed on it for approximately 1 year. And we hope to demonstrate that, and I think we already have somewhat demonstrated that bridges are an advantageous location to deploy tidal turbines. We hope that this deployment will help us gain insight into what it takes to operate a tidal turbine at a bridge. And this insight could be used for providing recommendations as to how you could best install one of these, a similar system to this at an existing bridge or the newly constructed bridge. So I now wanted to say thank you to the National Science Foundation, the U.S. Department of Highway, U.S. Department of Transportation, Federal Highway Administration, and the New Hampshire Department of Transportation for funding the construction of all this work, as well as my time here at UNH. This is our project website if you want to follow along the progress a little bit more. And I also have a small gift to give to my thesis committee. There's some 3D printed busts of my thesis advisor. is the big one.
I could so use one of those.
Yeah, I can take any questions. They're fully galvanized for erosion protection and to give them a nice metallic look. Yeah.
It's actually it's a history behind this. Somebody approached us to help scan an old half-hull model, which is at the FMA in Portsmouth. They used to build make these half-hull scale models, from which they then build full-scale ships. And he bought a little handheld 3D scanner for this, which he then afterwards donated to us. But it's a fairly inexpensive model, so it doesn't have enough resolution to really pick up on glass.
And I've got to thank Drum and Biles for helping me print those out.
All right, thank you, Ian. The thesis is open for questions. Actually, well, yeah, good try. So let me get started with the questions. So you selected a turbine that would give you roughly 1 megawatt-hour per month. That gives you the size, and then you go through this whole energy analysis, and you find that for reasonable battery bank size, it seems to home in at roughly the same size. Is that a coincidence, or is it?
Yeah, I guess it was slightly a coincidence. It also basically just helped to confirm that we had selected an appropriately sized turbine. Yeah, we didn't change our selection after we had done that analysis, but we also didn't end up going with that automated transfer switch system. But if we had gone with that automated transfer switch system, it would have shown us that our turbine was appropriately sized for that type of system.
It's not a coincidence.
Yeah, Professor Swift.
What was the load? You have blocks saying load. What is the load?
Which load?
The power.
Electric
Power. Same content.
Yeah, so the load is it's approximately 1 megawatt hour per month.
Yeah, you gave me the number, but what is it? What is it?
What's the load?
What's getting powered? Okay, so we're using a net metered system. So basically, if you live in Portsmouth, or anyone living anywhere actually, the electric grid doesn't care where your electrons go. But basically, our system is going to be grid tied and net metered. So the power will, whenever the bridge doesn't consume that power that's being produced, it'll actually be put out onto the utility grid. But then when the turbine isn't producing enough power to power the bridge, the utility grid will make up the difference such that we can keep all of our systems running.
What part of the bridge is being powered?
What devices are you powering with the?
Everything.
This is the
Lights? What's the primary load? How did you come up with that number?
The one.
Okay, so yeah, so that 1 megawatt hour per month came from the one megawatt hour per month. I didn't determine that. That came from a senior design project, and I believe that they looked at some of the utility bills for the bridge, and they figured out how much how much electricity the bridge was using every month, and they also estimated some amount of power draw from instrumentation that they expected was going to be deployed at the bridge. But in reality, the turbine will just be net metered, so it'll pretty much power anything that demands power.
But primarily, like it's the sensors, it lights. What on the bridge is it?
The 1 megawatt hour per month.
I know you're not metering, but when you were trying to just power the bridge before you did that,
Yeah.
what was it?
Okay, yeah. So yeah, it was all of the bridge. the lights, and some estimates for instrumentation.
That which makes the bridge live.
Yes, yeah. So that's why it's called the living bridge. This is how we fuel the bridge. It's the food for the bridge. Professor Foster?
Ian, I'm interested in the role of waves on these kinds of devices. So you're primarily considered the influence of the steady flow as it moves past the device.
Mm-hmm.
So what consideration did you give to, what kind of waves are there present? I know there often aren't waves. Are there times of the year when there are waves? If so, how big? What's the period?
Yep. So we did. I'm not sure if you're talking about power generation because of the way how that affects the power generation, or if you're affecting the loading. But I'll talk to you about the loading because that's what we kind of investigated. We used a 2.5 foot design wave, 2.5 foot wave height. We weren't sure exactly the wavelength that would occur, but what we did do is for those wave loads at our site.
Can I? So
Yep.
You're not sure what wavelength wave?
Yeah, because
Why is that?
we thought primarily the waves would be from ship-driven or like boat-driven waves, and different boats of different lengths traveling at different speeds all produce different wavelengths.
So there are no natural waves at the pier.
There are natural waves at the pier due to probably primarily wind-driven waves,
Yes.
but we have a really short fetch, so those waves typically don't develop to be as large as the boat-driven waves.
So what periods are those waves?
The wind-driven waves, we didn't look at that exactly because we thought that the largest waves would be coming from ship-driven waves, boat-driven waves.
So how did you determine if you had a force on a small body or a force on a large body? So when you did your Coolidge-Carpenter estimate, where were you? So how did you determine?
So another thing that I actually didn't, I'm not sure if it's in my additional slides or not, but basically I simulated the entire range of waves in all of those, in those charts. I did basically the full spectrum of waves in those charts, and we selected the highest force.
So based on that simulation, was it considered a force on a small body or a force on a large body?
Don't quote me on this, but I think I'm trying to remember.
Things not to say.
I can't remember exactly what wavelength came out to be the maximum wave force.
Well, I guess I'm thinking at a more fundamental level. I'm not asking that question specifically, but in wave forces on structures, you typically classify a body as a small body or a large body relative to the wavelength of the wave relative to the wavelength of the structure, so that you know whether you have potential flow around the body or you have vortex shedding around the body.
Okay.
So where did you end up?
So we didn't classify that. I would guess it's a large.
Which would mean there's no vortex shedding around that structure?
Due to wave. I think I'd have to get back to you on it.
Because your Coolidge-Carpenter cutoff, I think it's about 20 as you tip from. Professor Swift may have further information. I think it's about 20 as you go from small body or large body. So I would have thought that it would have been a small body and there would have been vortex shedding around it. But anyway, I can imagine that's going to matter. So that if this thing is deployed in big wind wave environments or even local sea states.
Oh, we actually looked at the waves generated by wind, and they were much smaller, even with the design wind of 45 miles per hour.
So I'm more or less thinking about the wave contribution to drag, and it's not, well, we can talk about it later, but I think.
Is it just a point where Duncan got involved in our discussions? I don't know.
Yes, but we could not come up with a good design condition on this, so we actually went back to, this is basically this goes beyond trying to figure out which the loadings is. We based all of the wave drag calculations on scale model experiments that essentially look at the range of parameters to get at added mass coefficients for full pairs of targets. And even in that, we didn't look at the carbon.
I was gonna say, so that's interesting. So if you did scale model, did you scale based on Carpenter?
We didn't.
Yeah. It's probably something, at least before I was gonna leave it out for a year, I would at least cross it off a list to know what regime you're in.
But in regards to wave-induced vortex shedding off the structure, we should check this, but I'm not concerned about it.
Will impact the performance.
Okay.
That's the question.
So I was more or less thinking about the design for the load, the structural loading on the mounts.
Yeah. Okay.
Okay, thanks.
Yeah, great.
So you kind of have a lifetime estimate of the platform? Like how long do you think it'll last before it just doesn't work at all?
So we need it to last at least that 1 year to deploy the turbine. I think it will last significantly longer than that. But yeah, everything was designed to ensure that that 1 year happened. Beyond that, just extra. Of course.
So you said you had to switch to a different turbine. You said you had some sort of adapter for what your original design was. How?
Okay, so
A little more info on that.
I guess we could go back to try to get back to where the turbines are. So yeah, the in-stream turbine uses, this actually is the in-stream turbine mounted on it here. And in-stream worked with us actually to design the mounting locations on that spanning beam. And essentially their turbine would just mount straight on top of, if this is the beam, their turbine mounted on top of the beam. New Energy Corporation, the way their turbine is set up is such that they have a beam that comes across and then their turbine goes right in the center of the beam. And their beam has some flanges on it that bolt right onto the mounting location of their turbine. The way we've adapted our system to mount their turbine is we've created an adapter that bolts on top of the beam, and then it has two arms that come down like this, and their turbine will fit right in the middle of those two arms, and then we'll bolts onto the adapter like that. And I designed that adapter for them and us when I was doing an internship at their company in Calgary.
Could you comment on how you adapted our turbine size, or how you made companies adapt our turbine size requirements
Yeah.
for respective rotors?
Yeah, okay, so the New Energy Corporation, or the, In-Stream Energy Systems turbine, originally when their previous deployment, they had a 3-meter diameter turbine rotor size and 1.5 meter depth. And so for our location, we have slightly slower currents than their previous installation. So we asked them if they could increase the height of their rotor, and they were able to increase the height of their rotor from 1.5 meters tall to 2 meters tall. And then things didn't work out with InStream, so we had to switch to New Energy. And when we switched to New Energy, their turbine typically has a rotor diameter of 3.4 meters in diameter, and a height of 1.7 meters tall. So it's a little bit wider and a little bit shorter than the what we were expecting to get from in-stream. The height wasn't too much of a big deal. The width was a big deal. Not a big deal, but it was something we had to work around. And what we ended up doing is we decreased the diameter of their turbine to 3.2 meters in diameter. It should be able to just squeeze through our moon pool. I think there's a few inches of play on either side, which that it will fit. And yeah. Ben?
What was your biggest challenge in this project? Like permitting, fabrication, design?
I mean, I think with a real life, with a project that's actually getting built, you're constantly just like running into the next like major extreme fire, and you're just like, what? This just keeps happening every day. So, but yeah, you just kind of learn to eventually just be like, all right, yeah, I'm just doing my job, and you just keep moving forward. There's tons of extreme challenges. I think the wave loading originally was a really hard challenge. That was something that I kind of started going in circles with originally, because I started doing the actual wave theory from the fundamentals, and I started really just going in circles until I posted on some forums online about just like this boat building forum, and I asked people like, how do you do this? And they were like, well, yeah, it is really hard to do this. You should probably just use some standards, some design guides or something like that. And they gave me a few suggestions, and then that made things a lot easier. So yeah. Sam?
Kind of along those lines, when we took FEA together and worked on that project for kind of analyzing the wave loader on that,
Yeah.
I didn't notice any. Did you end up using those, or was it
That's actually in the that's in my other questions that you could ask me about during the additional slides if you want. Yeah, so we did do some analysis on the frame wave loading. So basically like the racking of the frame. If you get waves coming at a 45-degree angle to your platform, you might get a situation like this kind of starting to go on. And yeah, we used some DNVGL. It's a Marine Classification Society, and they basically give you some standards for determining some loadings that you can apply on your structure when you're analyzing it to help determine if it's going to start holding up to those wave loads. And then I performed some FEA on it. Aaron's students also performed quite a bit of FEA on it to make sure that we would be able to handle these loads.
Cool. There's an estimate of wavelength in the picture.
This wavelength?
Yeah.
If your wavelength matches the length of your structure, or the length of your structure along the...
It was all implicit in the design plot earlier. You had your wavelength versus structure length of multiplication factor.
Yeah, these are actually two different design scenarios. This is for the basically the racking. What I showed you earlier in the presentation was for like kind of that horizontal force that would be applied to the vertical guideposts. In this situation, the way DNVGL has you do it is they make you, I think probably your wavelength is wrapped into this a little bit. They make you kind of classify, where is your structure going to be used? Is it going to be used really inland? Basically, if it's going to be way out in the ocean, that's a much different wave environment than if it's going to be used kind of inland where we're operating. There's also some stuff about your like maximum estimated craft speed in those design standards. Yeah.
The color plot there, moment?
Yep.
What kind of moment?
So it's the
moment applied by the wave, and did you use that as the loading for a structural analysis?
Yeah, so what's shown in this plot here is, I believe, the MS load case, which isn't even shown in this diagram here. But what it is you fix this side of the platform, and then it's essentially the entire platform is a cantilever beam. So DNVGL tells you what amount of force to apply on this side of the frame. Then using another design standard, the American Institute of Steel Construction, you can determine if you're using standard like shapes, like standard I-beams, which we did use in our construction. Different shapes have different moment allowances that you can load them to. So for our I-beams, I don't remember what the allowable moment was, but we basically needed, that was our failure criteria in the finite element analysis. So typically in mechanical engineering, we do use von Mises stress as a failure criteria. Aaron doesn't like that. But if you start trying to resolve the von Mises stress in a structure like this, well, first off, you can't do it with beam elements, which is what we were using in this simulation. Also, if you were to do it in a structure like this, you would very inaccurately resolve the von Mises stress in locations in your connections. So a simplification is to calculate the maximum moment in the various portions of your structure, and then use the maximum allowable moment from the AISC standards as your failure criteria.
Doesn't this have to start with some assumption regarding the incident wave, a value for wavelength, a value for wave height?
Yeah, so that comes from where in DNVGL you classify your structure and where it's going to be operating. You don't ever, with the DNVGL standards, you don't ever actually put in what the wave height or wavelength is. It's just you kind of say all right, it's going to be operating in these types of waters. It's going to be in a harbor. I think the parameters they use is it's going to be in a harbor. How far is it to its safe mooring location, and how fast is it going to travel? Those are kind of the parameters that they use for their empirical model.
Did they also use wind in there?
There wasn't any wind loading in this scenario. I would assume that's kind of wrapped up in their, I'm not sure, it might even be, no, I don't have it in my next slide. Basically, there's different, they basically kind of break it out, I think, into about 5 or 6 different operating regimes. One would be way out, open ocean. You can go for days without, probably go for weeks without ever coming into safe harbor. And the thing is going to be able to travel pretty fast. I don't know, 30 knots or 20 knots or something like that. That you would have to design for much stronger wave loading on a craft like that, rather than a craft like this, which is maybe only going to go 4 knots at maximum speed. And then it's going to always be used within a harbor, and yeah, it will never be less than a few nautical miles from its safe mooring location.
I think the important part is here is that this was analyzed in 2 different ways, right? So first we calculated all these forces explicitly, and then after we went through all this, we also checked the standards and found that, okay, under their, very conservative loading scenarios, it will also. So it's really.
I think the standards are.
This was separate from what you showed before.
Yeah. John?
What's the drag force of the biofouling, and how does that affect your drag on the platform? I mean, is that a concern?
Yeah, so we didn't account for biofouling in the drag on our structure, but I can tell you that the the estimation of drag force on our pontoons was rather conservative. We did assume that our pontoons were fully submerged, where hopefully they're never fully submerged, because that would mean our platform is underwater. So I think that biofouling drag can be wrapped up into some of the conservation allowed for some of the other calculations.
All right, any other questions? If not, then I would ask everybody except for the committee members to excuse us for a moment while we deliberate. Actually ask Ian some more questions. The hard one.